Look what's arrived. Yes, Christmas has come early to Hamilton in New Zealand, and I've received my transformer. Well, it's not all 100% good news, but it's 95% good news. Now, I originally mentioned in the previous videos that I was looking for a transformer of 24 volts, 24 volts and 160 watts. Well, I know New Zealand's a long way away from anywhere, but the delivery on such transformers is just that the date just kept on going and going and going. So bearing in mind what this is going to be used for, i.e. monitoring video output largely, I've decided to downgrade it slightly. Now, if you've watched the previous videos, and if you haven't, why not? Amazing entertainment. Anyway, we won't go there. So what I've done, bearing in mind how pleased I was with the results from that small 30 watt transformer, I have downgraded the transformer to 120 watt, and also the voltage was going to be 25/025 AC, of course, but that is now 24/024, so the actual output power will be less than I originally anticipated, but I don't think that's going to be an issue. Now, forgive me if I'm going into the detail of how to connect this transformer in too much detail. I know some of you are going to go, oh, doesn't anyone know how to connect a transformer? Well, the answer is no, a lot of people don't know how. So the first part of this video is going to be how to connect this transformer for this and any other project that uses a toroidal transformer. So let's get on with it. Now imagine you're going to connect this to 240 volts, as indeed I am. The 0 volts, or the live if you like, will go into here, and the neutral will go into here, and we have to link the grey and the purple wire, like so. But if you're in America or anywhere else that uses 110 volts, these two windings will be in parallel. So you would connect the blue and the purple for live and grey and brown for neutral. So that's how you connect the primary, and it's best to measure it out and see. And I will do that now and put in some typical values. Right, I've measured the primary and secondary, and on the first winding you have an 8 ohm resistance, and obviously the same on the second. And if you've connected it correctly for 240 volts, these two will be in series, so you'll see about 16 ohms on the primary. And the primary tends to be the higher of the resistance because the wire is thinner and many more turns. Now the secondary, this is how you connect it. This doesn't matter whether you're, whatever the primary is, the secondary will be the same, because we want 24, 0 and 24. Now obviously if you connected your meter across those two, you would have one voltage of 48 volts, which in this case we don't want. So you connect the end of one winding to the big start of the next winding. Link that together and that becomes your 0 volts. And then this will be your 24 volts, and this will be your other 24 volts. Now this leads off to the rectifier and smoothing circuitry. Now the first thing I'm going to do with this transformer is lengthen these wires. Now there's a very good reason for doing this, and I'm also going to connect the various links between the windings, because a toroidal transformer has a number of things that it's sort of well known for, and the main one is it has a low radiated field. Therefore you can tend to use it with much lower hum pickup than you can with a standard transformer. But that is only half true. Where the wires come out, the field tends to be concentrated. And I say tends because there's exceptions to every rule. So if you're going to mount this in close proximity to some circuitry, you want to be able to rotate the transformer. And that's why I'm going to lengthen the cables. And when I've found the ideal place with zero, preferably, or minimal hum pickup, then I will bolt it down, shorten the wires appropriately, but don't try to do it with the wires that come with it, because you'll find that you'll turn it round, they'll get all tangled up and you'll end up with problems. Take it from me, I've done all this before. So lengthen the cables, not by a huge amount, probably about 6 inches, and locate the transformer, like this. Let me show you. Right, here's our simulation of what we're going to do. Incidentally, the wires should be at the top. You don't really want the wires trapped underneath the transformer. So you connect this up. Now this assumes, of course, that everything has been tested with the amplifier, with the transformer, and virtually the last thing you want to do is to mount the transformer completely. So this is what I mean by just rotating it. It's self-explanatory. You just wire it up and rotate it. The amplifier is switched on with no input. Volume, it doesn't really matter where the volume is, but preferably with the volume turned off, because you want to see if the transformer is inducing magnetic field into the amplifier, or even the inputs here, because with any of these sort of projects, space is always a premium. So rotate the transformer, mark where it is so you know where to connect it, and then continue the project. Now, when you order your transformer, make sure the kit includes the mounting pack, which is this. Without this, you really have a problem mounting it. And what you should get is a metal, usually steel, what you call it, a washer of some sort, and 2 neoprene, usually could be rubber, and usually quite a pungent smell. 2 of those, a large bolt, and a couple of washers, a spring washer and a nut. And this is how you mount it. Here is our transformer, and the first piece that goes on is it sits on one of the neoprene washers. Then the other neoprene washer goes on the top, and then the metal washer goes down like that. And then the bolt goes through the middle with the washer and a spring, little spring washer, preferably the other way around actually. Says here dropping it on the floor and never finding it again. And we'll find that in a minute. And then that drops through the whole thing. So you end up with this. You can see how that is. That goes through there. Now you must make sure this goes through the center of the transformer and doesn't in fact scrape on the windings, because you could be in for a nasty shock. Then you drill a hole in your chassis, slightly bigger than that, drop that through, and then the nut goes over there after you put an additional washer on. And that's how you mount it. Now, there's a couple of things you should know, which, if you don't know, this could save your project and a potential fire. If you think about it, a toroidal transformer, the windings go round through the, let's take that off. The winding goes through there, down and up, and the next one comes up like that. So the windings go round the transformer. Now, if you put that through the center and join that to the metal chassis, If you happen to touch the top cover to this, you've effectively made one turn of wire going completely round the transformer. And as it's heavy gauge steel, and the chassis could be made of aluminium or steel or something like that, the voltage it will induce into that will be very low, probably about 1 volt. But it will be at probably maybe 100 amps. So the result of that is the transformer primary will heat up, and this could glow red hot. And the next thing you know, if it doesn't, it may not even blow the fuse, because although 100 amps sounds a lot, at 1 volt it's probably still under the rating of your fuse. So you must make sure that the metalwork or anything else metal never comes in contact with the top of this transformer. You'll only ever do it once, but it could be a very expensive and potentially very dangerous thing to do. And in an ideal world, this metal shaft should have a break in it or be made out of a material other than steel. But in practice, they're always made like this. And you'd actually be better off with a piece of wood, to be honest, because wood doesn't conduct electricity. So be conscious of that, because it's a very expensive, potentially lethal. You could burn your house down. Right, I've made the mock-up for connecting and testing the transformer. This is the primary, and I've got the 2 center windings in series and isolated here with shrink wrap, and these are the 2 AC inputs for 240 volts. As I explained earlier, this is different if you're in 110 volt areas. This is the secondary, and I've just linked some wires on temporarily. The 2 browns are the positives, so to speak, and the black wire is the center tap negative. So when I connect the meter from here to this brown lead, I should have about 24-25 volts. It will probably be in excess of that, because this is a 230 volt transformer and we've actually got 240 volts today, so it's going to be running slightly high, and the ratings of most transformers tend to be off load, or I should say the ratings tend to be at the rated power. So although this says 24 volts, I would expect it to be probably a volt or 2 more than that, because obviously I've got no load here. And when we go across the 2 brown wires here, we should get the full voltage. So we'll put the meter on it and have a quick test. The meter's on the AC 200 volt range, and this is the meter connecting here. It looks a bit of a spaghetti, but it's purely on an extension lead, so I can clip the crocks on the bare wire. So we'll power up now, and this should get somewhere in excess of 24 volts. I'm expecting something like 25, maybe 26. Well, it's a little higher than I anticipated. It's supposed to be 24, but as I said, it is off-load with a slightly higher mains than standard. So we'll whip the power off and check the other winding, and that should be, well, hopefully pretty well the same. Yep, exactly the same. The thing that I should mention before we go any further is the quiescent current on these amplifiers should be turned to minimum. So using a suitable tool, you need to turn this pot down to absolutely minimum, because with this extra voltage on this, we have no idea at this stage what the quiescent current's going to be. So I've already done this. I've turned it down to minimum, and if we look at your voltage here, our DC volts is actually plus and minus 37.5 5.8, and that's with virtually no load. So you're allowed 40 volts, so we're well within the ratings. It's been on for a while now and there's no smoke coming out. And if we look at the scope now, there we are, just below clipping. And we look at the voltmeter, this is RMS. We're on the 30 volt scale, so we have actually 20 volts. And that is 50 watts per channel. Now as yet, that is with very low quiescent current. So we've got to measure the quiescent current now and adjust it similar to what we did in the previous video to obtain no crossover distortion. Now I would suggest I'm not going to measure this into 4 ohms because I really don't think the heat sinking on here is adequate for 4 ohms. Oh, to hell. We'll measure it quickly, but it won't be left on for very long. Well, I've done some 4 ohm tests and we get 72.25 watts. Not bad, but I must say that it does get quite hot quite quickly. So I would not really recommend sine wave driving with this kind of heat sink, or lack of heat sink for that matter. But 8 ohms, it will be fine, giving 50 watts. And again, this is testing it with a sine wave. In music, you'll be using 75% less power on music, so I think it will be absolutely fine. All we've got to do now is check DC offset and adjust the QI pots and do some rotation of the transformer for minimum or preferably no hum. We've got the meter on the DC 200 millivolt scale and we're going to check the left channel. Hope my hand's not in the way. 5.2 millivolts, and the right hand channel, how can I do this without getting my hands in the way? Slightly more, 8.4 millivolts, but still a very respectable number. I use a very high frequency, in this case 30 kilohertz. Is it 30? In actual fact, it's not 30, it's 60 kilohertz. I got a bit carried away here, but it matters not. Theoretically, the higher the frequency, the better. And I've taken one of the supply leads from the rectifier board and broke it and put the meter in series. It's on the 200 milliamp scale, and as you can see, the waveform looks pretty dreadful. So I'm about to wind up the pot. Now, bearing in mind there will be the quiescent current is actually a little below this because obviously I'm producing some power and you normally wouldn't be doing that. So what we have to do is turn up the pot and watch the waveform and make sure the current doesn't go into some ridiculous figure. So here we are, we're starting to see an improvement, and it will happen all of a sudden. There you are. Now what we have to do now is remove the signal. So I'm taking the signal off, and this is the total power consumption of that channel. Now that is a little bit on the high side, so I think we're going to have to take that down a bit. So let's put the signal back on. You can see it doesn't go up very much because we're operating at such a low level. So we will wind the current down a fraction because we won't be doing much listening at 60k. You can see now we've gone down to 26 and there's just the merest hint of crossover. Right, I realised that I was being a little bit silly there, so I've reduced the frequency to 20 kilohertz. But I'm going to reduce the quiescent current even more, and until, let's expand it. Everything else is the same. The power is minuscule low. Let's increase the, now you're starting to get lots of noise now, but that matters not. So we'll reduce the quiescent current a bit more. Oh, there you can just see it beginning to notch. So it looks like we've got, let's increase that a bit. And that's a current drain of, we call it 24 millivolts. But if we reduce the signal, and we'll turn the signal off, that's our real quiescent current, which is just under 20 milliamps. So it rather looks like we can set this to 20 milliamps as a nice round figure that won't make the amplifier run hot. It's actually quite critical when you get to this part. So we'll take that down to 20 millivolts. We've got no signal on now. That's as near as damn it 20 milliamps. And when we put the signal on, of course, the current will go up because we're actually burning power into the load. But that's a very, we're now, that's still, I know you can't see the other meter, but that's now, do the maths in your head, boy. You can do it. That's 100 milliwatts into 8 ohms. And I would suggest there's no crossover on that we need to worry about. Right, well, I think I've pretty well settled on 20 milliamps. What I'm going to do now is to drive it hard for about 5 or 6 minutes and really heat it up, and then come back to see what the quiescent current is doing. I mean, perfectly, it should drop back to 20 milliamps quite quickly, but we shall see what will happen. So we'll be back in about 5 minutes. Right, I've been driving this now for about 5 minutes at 20 kilohertz at near full power, probably about 45 watts. And I've just literally switched it back on again with no signal, and the quiescent current has gone up 1.4 milliamps. And the heatsink is actually, well, the heatsink, the side of the case, is almost too hot to touch. So I'm very pleased with that. There's no hint of thermal runaway. So all I'm going to do now is do the same thing to the other channel, rotate the transformer to make sure there's no hum coming from it. Right, we're just going to measure the input sensitivity now. There is clipping. We're on the 30 volt range RMS, and we call it 20 volts. So this is the input, and it's on the 1 volt full scale, so the top scale's here, so it's about 740 millivolts for 50 watts into 8 ohms. A quick look inside to show you how the transformer's mounted. And one thing I should have said, when you mount this transformer, people often ask how tight it should be. Well, it should be just tight enough that you can't move the transformer. You don't want to grip it down so that it sort of forces the windings on top of each other, and you could end up with a short. Now, I didn't want to shorten these wires too much. These ones I had to lengthen, hence this. But the mains ones I've just bunched up, simply because this will probably be in another project in a few weeks' time. I don't know, but you never want to crop the transformer leads short. What do I think of it? Now, for the purpose that I made it for, monitoring video, pointing to the right place for a change, it's perfect. And I have to say, with the higher voltage from the transformer that we've got now, as I mentioned before, it does produce 50 watts per channel, but you can't possibly test it sine wave for any length of time, because the heat sinking, which as I've shown you is just basically the case of the project, it gets very hot very quickly. But there again, apart from the initial test, why would you be sine wave testing it? If you're going to use it purely for music, which I have been using, spent most of yesterday and the day before listening to it in the lounge on my Monitor audio speakers. More about the sound in a minute. And it gets warm, certainly not too hot to touch, and that's giving it a fair bit of stick. But for normal listening levels, it only gets slightly warm, so there's no issue there. I've got no hum from the transformer, no hiss, and overall I'm pleased with the project. But what I have to comment on is the sound of the amplifier. I have to say, of all the amplifiers of this category that I've built, it's my least favourite. Now, without fear of upsetting too many people, it sounds more like a valve amplifier. Now, anyone that knows my channel knows that I'm not a great lover of valve amplifiers. This amplifier, going back in history to when I know this is a clone and how close to the original Naim amplifier this is, I suspect not very. But as I mentioned before, possibly, can't remember whether I did or not, I used to be in the hi-fi business, retailing and manufacturing hi-fi, and I personally never liked the sound of Naim amplifiers. I can't tell you why, because it was about 45 years ago, and any of the Naim's later products I can't comment on because I don't know. But certainly when I was in the business, I didn't like the sound of them. They sounded more like a valve amplifier. So if you like the sound of valve amplifiers, you might well like the sound of the Naim. But a funny thing, yesterday I went out to the post box and I left the music playing in the lounge, and my wife came home, and as soon as I got in the door she said, "What's happened to the amplifier?" And I thought, oh God, are we on fire? And I said, "What do you mean?" She said, "Oh, it doesn't sound very good." And I said, that's the new one, because normally this has just been sitting on top of the L12, which is still my favourite amplifier. And bearing in mind she's not a terribly wonderful audiophile type person, she likes the music to sound good, but I was amazed that she noticed that it didn't sound very good. And I tried to get some superlatives, I can't say the word even, out of her, and she said the sound just sounds all muddled up. The L12, it sounds like you're in the middle of the music rather than it just being muddled. And I have to say, that's what I think about it. So in order of the amplifiers that I've built so far, the very first one was the MX50, I think it's called, which was about the same price as this one and beats this hands down. The Class D one was okay. The L12 Mark II is my favourite. It's got so much dynamic range, and the reason I'm going into this a bit and waffling along a bit is because I get asked this all the time. People write to me and say, "Oh, I see you've got this, what do you think? I've got this, should I change it?" And so really the L12 is the one that I like the most so far. Now tomorrow could be a different story. I'm always looking for new modules, but bearing in mind these modules are cheap to build, and we're getting 50 watts per channel, which is pretty good power. And in fact, if you wanted to get the full 80 watts that the module claims it will do, It just needs more volts and a bigger transformer. Simple as that. I've got 35, 36 volts, plus and minus, and I think it asks for 40 volts. I can't remember, but power will depend solely on how many volts you throw at it, and assuming the transformer has enough amperage or wattage to deliver that without the power dropping too much. Anyway, that's the end of this series, and I'll speak to you again when I've got something slightly interesting to tell you. Thanks for watching.